Okay, so we already studied the basic behavior of a structural member, stretching behavior, bending behavior, and twisting behavior. These three are most basic behavior. So today I like to talk about really important principle in structural mechanics. Okay. Principle of virtual work. So some of you already heard about that principle of virtual work or already studied. So today's topic is this one. So today I like to drive the principle of virtual work. You have any idea about principle of virtual work? 정호? Any idea? You studied already in undergraduate school, right? What's the principle of virtual work?
It is make displacement, virtual displacement, and consider energy is same.
So maybe you know the concept. So you mean applying some virtual displacement and calculate the internal and external energy, right? And both should be same. Okay. First of all, let's consider the problem description. This is a body we like to consider, and usually body is prescribed, so fixed. This is a surface where body is fixed. So volume of body is omega 0, and this part, fixed part, omega ud. ud means the displacement is prescribed on this surface. And other surface can be, and this will be deformed. Somehow, there will be some deformation. This is a deformed configuration. Of course, to make this body deform, two possible external load exist. One is a traction applied on the surface. It's a surface force. You can just think surface force. And the other is a body force. Body force F. Right? And let's think this part where the surface force is applied is a place TD. So how about the remaining surface? You can consider this remaining surface is also force boundary. Okay, where zero surface force is applied, right? Okay, and so total surface will be sum of both equal boundary surface, displacement boundary surface, and force boundary surface. Right? And let's define surface force. Surface force with a vector T, D. Okay, so T1D, T2D, T3D, something like this. And body force. F1, F2, F2, 3. So, common body force is gravity force and inertia force due to the acceleration of the body motion. Okay, here this is a displacement boundary. This is a force boundary. Okay. Of course, to define the component of surface force and body force, we need to define the coordinate system, right? E1, E2, E3. So X1, X2, X3. So here, component of body force F1 mean the direction of the force in E1 direction. And this T1D component mean the direction corresponding to the E1, right? Something like this. Okay, then displacement. So displacement is also vector. So E1 direction, E2 direction, E3 direction. So U1, U2, U3 are component of displacement vector. And let's define the stress. Stress is a tensor, right? 1, 1, 1, 2, 1, 3, 2, 2, 2, 3, 3, 3. This is symmetric tensor. Symmetric, right? So now we define the problem. The coordinate system, original configuration, and current configuration, okay, and displacement boundary, force boundary, and surface force, and body force, and displacement, and stress. Okay, so we define all the variables we need to solve this general problem, solid mechanics problem, right? So, geometry and material property and boundary conditions are given, right? So, we need to solve this problem. To find what? What should we find in this problem? Yeah, right. We need to find solution. What's the solution? Solution is a displacement, unknown, right? Displacement, stress, strain, right? If we know one of these three, we can calculate the other two, right? Once we know displacement, we can easily calculate the strain and this stress. Once we know stress, we can calculate strain and displacement. Because these three have a relationship, right? So, The goal is to find the solution. The solution need to satisfy. So here solution is U. This is solution, right? Solution need to satisfy governing equation, right? First, equilibrium. In the body and on the boundary, right? Especially on force boundary. First, equilibrium should be satisfied. So, there are two equilibrium. One is in the body, so we can write down, we already know this equilibrium equation, equal 0 and equal T, right? Or stress Ij, J plus Fi equal 0 in the body, or stress Ij and J equal T di in the force boundary. This is an equilibrium. Okay, here stress Ij, J equal Ij x J. Okay. So equilibrium should be specified in the body and on the surface. This is one of the governing equation. Second, so compatibility T on S so this is displacement boundary condition. So displacement boundary condition mean U bar the displacement 0 or Ui equal 0 on displacement boundary, right? Because the on the displacement boundary, displacement is fixed, right? So this condition should be satisfied. To get rid of the rigid body motion, right? So structure should be properly constrained, fixed, right? And third, stress, strain, low, right? This is material law. So stress is a function of strain. So for linear elastic isotropic material, we can have this simple relation, or stress Ij Cijkl. Here the C is a force of the tensor. Which represents the material law, right? Any question? Here? Right. Okay, so UD. Right. Okay. So, here the main equation is the first one, equilibrium on the body, right? And this, what's this? This is force boundary condition, right? Force boundary condition. And this is a displacement boundary condition. And this is just relation between statics and kinematics. Stress and strain, material law. So, solution should satisfy all of these. Otherwise, in other words, if we use these three equations, we can calculate the solution, right? Okay, so let's start driving the principle of virtual work. The starting point is equilibrium equation. Stress Ij J plus Fi equal 0. This is equilibrium equation, local equilibrium equation. This equation should be satisfied all the material point in the body, right? You remember? So in all the material point, this equation should give a 0, right? The left hand side of this equation should be 0, right? Okay. Then now, I like to multiply something here. Okay? Yeah. I like to multiply something. You can say some arbitrary value or here. Then it should be 0 too, right? Because this part is 0, right? Zero multiplied by 1,000 is 0, right? 0 multiplied by million is 0, right? Always 0. So here we are multiplying some special thing. Its name is virtual displacement. Virtual displacement. Okay. So we are multiplying the virtual displacement. It has a very important feature. So this is 0. It has a 0 value on displacement boundary. Okay. Okay, sorry, I have here. I don't have it here. And arbitrary means this value can have anything. So, but continuous. So this is UI, this is vector, right? So some vector field is multiplied to this equation, right? And that vector field is zero, has a zero value on the displacement boundary, and it can be arbitrary and should be continuous. So, okay, so I like to give you concept. This is on the original configuration, and this is deformed configuration. And in this deformed configuration, we are giving some arbitrary shape of, okay? This is arbitrary shape of UI. Displacement. This is virtual displacement. And this vector field satisfies the zero on the boundary, right? Displacement boundary, UD. And its shape can be arbitrary and continuous. So, for example, let's say this is the deformed configuration. And this type of virtual displacement is okay. But how about this type of virtual displacement? Is it okay or not? No? This type of virtual displacement does not satisfy the boundary condition, X. How about this? Virtual displacement, something like that. So, here. It's not discontinuous, right? This is the X. So just think, there is a local equilibrium, and we are multiplying some special vector field. It's named virtual displacement, okay? And that virtual displacement is zero on the boundary, displacement boundary, and it can have an arbitrary shape, but should be continuous. Okay? So one of the very interesting things is what's the left-hand side? This is force. Okay? What's this? Displacement. Even this is virtual, so the name is displacement. It's a force multiplied by displacement give us some energy, right? So you can think here the left-hand side give us some energy, right? Okay. Now next step, let's integrate the equation. Stress Ij J plus Fi Ui d omega. If I integrate that equation, that it should be 0, 2, right? Because inside of this integration is 0 for all the material points. So even I integrate this equation, it should give us 0, right? It's too simple, right? And let's look at this equation. Let's look at this equation become omega ij j ui plus fi ui d omega equals 0, right? Now we need to do some mathematical thing. Okay, let's look at this side. Uij. If I differentiate this equation, what happens? About j, I like differentiate this. Then it become ij j. I should differentiate first one, then second one plus ij ui j. Okay, so this term is same to this, right? So instead of this term, we can use this one and this one, right? So let's use this is a name integration by part. So that equation is changed by integration by part. ij ui j minus ij ui j plus fi ui. d omega equals 0. This is a form we have right now. So we have a 3 form here. This one, this one, this one. Let's say first one is a 1, 2, 3. We have 3 terms. Can you follow me? Okay. Then let's look at the first term. First term, omega, stress ij, ui, j, d omega. Right? This is integration in the volume. Right? You know that the integration in the volume can be changed into integration on the surface. Okay? So, this equation can be changed integration on surface. Integration on surface. How? Stress ij delta ui nj d surface. You know this rule? Okay, I like notes. Very well known divergence theorem. Divergence theorem. Here, let's say we have a domain here. Okay, domain has a volume B and surface S. Okay, and this domain, there are some vector function A. So on this, in this domain, vector function A exists, and normal surface vector is n. Then divergence theorem gives us this relation AI I D dB equal S AI Ni ds. So integration about the volume is changed integration about the surface. Here AII means AII equal partial XI partial AI, right? So using this divergence theorem, here the equation 1 is changed to the integration on the surface. If we use this, we can calculate the volume of the body, right? Okay, then this is divergence theorem. And here, let's continue to derive the equation number 1. So this is the integration on the whole surface. So that equation can be divided by 2 parts. Integration on force boundary, Ij, Ui, and J, ds, plus integration on displacement boundary. Right? And you remember when we designed the virtual displacement, I said we used virtual displacement field which is satisfied the displacement boundary condition. So virtual displacement gives us 0 value on the boundary. So this is 0, on UD. So second term becomes 0, right? Right? Then how about the first term here? Here first term have a, so it become only, we have first term TD. So if I rewrite IJ, NJ, UI, DS, right? This is a force boundary, right? So here we can give us equilibrium equation NJ equal TDI on TD, right? On the force. I can impose force boundary condition. Then it becomes TD, TDI, and TD, sorry, HJI. So this TDI, okay, UI, DS, right? So finally, this term become changed. Become simpler. So if I use that result, this result, I can rewrite this equation. I can rewrite. Here the second term is a minus. So let's move this term to the other side and stress IJ U I J D omega equal Fi Ui d omega plus dd ui ds. This was originally 2. This was originally 1, 3. This was originally 1. Okay. So we can rewrite the equation something like that. We have 3 terms. In the left-hand side, we have 1 term. Right-hand side, we have 2 terms. Both sides should be same. So to drive this equation, we start from local equilibrium equation. Then also we already used the equilibrium on the surface and force boundary condition, displacement boundary condition. So we use the equilibrium equation, force boundary condition, displacement boundary condition, right? Okay, then let's look at the equation, second equation over there. Stress ij, u, I, j. Let's look at this. This become stress ij 1 over 2 u, I, comma j plus u, j, comma I. Because stress tensor is symmetric, right? Looks tricky, right? If you expand both sides and compare, then you can very easily identify here left hand equation, right hand side equation are same. Okay? Both are same. And watch this here. Looks like small strain. So it become stress ij and virtual strain ij. Here where virtual strain ij 1 over 2 u ij plus u j I. This is a virtual strain. Okay. Okay. So we almost derive the final equation. Then finally we can derive the equation omega stress ij d omega equal fi ui di ui ds. This is the final equation. We are saying here the left hand side is an internal virtual walk, right hand side external virtual walk. Virtual walk. So external virtual walk is the same to the internal virtual walk. So here I multiply stress and strain. Actually, virtual strain, it's not a real strain. You should remember, this is not a real strain. Virtual strain, right? Virtual means not actual, okay? So not real. So here stress is real, okay? This stress is real. Force is real, okay? But this is virtual displacement, not real. This is virtual strain. It's not a real strain, okay? So, but this is stress, virtual, strain, right? So both will give us energy density. And if I integrate on the volume, here the left hand side give us something like energy or works. But it's not real work, right? Virtual work. So left hand side is internal virtual work. Right hand side also force displacement. It gives us work, right? But it's not a real work because this work has been done by virtual displacement, not the real displacement. So we are saying virtual work, external virtual work, because this is external force, external body force, external surface force. So external virtual work. Here, stress is internal force, right? So internal virtual work. Okay, and then this equation can be used the linear and nonlinear analysis both. Okay, material nonlinear, plastic analysis, or large deformation analysis, large strain analysis. This is a very, very general equation. It can be used for linear and nonlinear. You should remember. But if we limit the use of that equation for linear elastic case, linear elastic case, we can use a material law Ij equals Cij KL E KL. Let's put yield this equation over there. Then we can have an internal virtual work EKL Ij KL. Okay, so let's check. Eij, okay, Cij, KL, EKL, d omega equal other part are same. Okay, same. This is a principle of virtual work for linear elastic case. This is a principle of virtual work for general case. Okay. Okay, so today I drive the principle of virtual work. This is really, really important principle. It's a kind of energy method. We can use this principle to solve solid mechanics and structural mechanics problem. So I'm going to show you the example, how to use this equation, okay? Through some valuable example. So any question?